Welcome to the course CBS VLSI Design. In this week, we are going to discuss about hardware security and how high level synthesis can help in making secure hardware. Okay. So, in this particular course, we try to mean by hardware security is the security concern that is coming because of this globalization of the IC design flow and whatever the risk is coming and how we can actually solve those security issues in high level synthesis. Okay. So, I want to acknowledge the authors of this paper because this particular lecture is primarily adapted from the slides of this particular paper given by these authors. So, let us try to understand the IC design flow, right. So, the primary motivation is that if you have a chip, you have a specification, right. So, you have a specification and then you have to do the synthesis, which part of this high level synthesis, logic synthesis, physical synthesis, and then finally you will get the layout and then you have to fabricate it, right. So, the IC is something after fabrication only you will get the IC. So, that is the overall idea of the IC design flow. So, if I just go into bit details, so as I mentioned that nowadays the chip is not a single thing, it is a SoC, right, system on chip. So, you need multiple IPs. So, you bring the IPs from different vendor and those vendor might use they develop that IP, they give a RTL IP, right, and this IP may be developed directly by writing the HDL or you write C code and then you use high level synthesis to generate those IPs, right. So, you have different component you brought from different vendors and then you integrate them and then after integrate you integrate the things in the register transfer level. So, you have the RTL and then you do this logic synthesis which will convert the RTL into gate level and then you do the physical synthesis which will convert this gate level into transistors and also it also place the transistors in a particular specified area. It also place the interconnections between the transistors. So, it give you the layout, right, so which is a very common format is GDS2 format, okay, and that layout is given to the fabrication lab. Right. So, the fabrication lab is something where actual this layout is physically realized in a IC, okay, and then you will get a chip. Once the chip come, you have to test whether is there any malfunction and then once you found that your chip is working fine, then you do the packaging, assembling, you get the IC, right, integrated circuits, and then you combine into a bigger system PCB and then you have the system, you port it to the customers, right. So, that is the overall the IC design flow, okay. So, before globalization, so what usually happened, the whole flow was having inside a particular single company, right. So, you have a single company which have all these facilities, right. It has a team to develop IPs, it had teams to develop the integrations, it has softwares to convert these things into logic synthesis, physical synthesis, all the software they have, and then finally, when they have the layout, they actually have the fabrication lab also, right. So, they have the complete flow and then they have the test engineer, they have the assemble packaging engineer, then they integrate everything and they have the the complete system developed in house and it was shipped to the customers, right. So, it's basically there is no risk of having their intellectual properties leaked to somebody else, right. So, everything inside a single company and there is no risk, right. But because of this globalization and the tremendous growth of this IC industry, having the whole, we have lot of companies coming up, right, and having this facility in a single company is become impossible because this specifically this fabrication is lab is way expensive, right. So, that kind of model does not survive. So, what the model comes up, that we have a dedicated fabrication lab, right. So, that will just do the fabrication. There are dedicated companies who just develop the IPs, right. So, they have the experts, the RTL engineer or engineers, they just only create the efficient IPs, right. So, and then there are many such companies. So, there are companies that exist who actually develop this efficient EDA software for the logic synthesis, physical synthesis, high level synthesis, right. So, it basically get globalized, right. So, there are experts, right, there are domain experts for EDA tools, there are expert for IP developer, there are some and then the EDA companies or this chip design companies, what they do, they buy the IPs from the vendors, they buy this EDA software from the EDA software tool provider, and they just integrate the overall things into one, and then give the complete thing to the fabrication lab, right, because they do not have the fabrication facility. And then the fabrication lab actually fabricate the IC, and then it gives back, and then the packaging, everything happens, and then it comes to the customer, right. So this is the feasible options, and that is what is happening in nowadays, right. So, but what is the problem with this? So, you can see here that a IP engineer they are giving the IP to this design house, and this whole thing, this after layout, everything, the layout is given to the fabrication lab, right. So, that means you are actually revealing your intellectual property to third party, right. So, and that might be costly, right, because there might be somebody in that fabrication house who are not, say, trusted employee, and they might do something to your intellectual property, right. And then we will see, because so what are the security concerns come because of this globalization of the IC design flow. Okay. So, the first one is the hardware Trojan. It is very well known that hardware Trojan is something, a malicious modification of the design, right. So, so you as I mentioned that you have the SOC integration house who actually integrate the IP taken from the different vendor and different SOC, and that was given to a foundry, right. So, now this foundry might have some malicious employees who might actually insert hardware Trojan in your design, right. So, and the hardware Trojan what it does, there are two type of hardware Trojan. One is basically leaking sensitive information, that might leak some sensitive information through something, or it might modify the circuits also, right. So, there are two type of hardware Trojan available, and basically this hardware Trojan gets activated in a very corner scenarios, right. So, like this, if the possible input is say specific pattern, then only this hardware Trojan will be activated, or say it will be activated after 1 year, right. So, this kind of trigger condition is something, it is very corner cases. As a result, even if this malicious modification happened during testing or any other process, you won't able, it will be hard to detect those hardware Trojan, right. So, they will actually bypass the whole checking process, and then it will go into the customer side, and that they might do the damage. Okay. So, we already have many such incidents, and the interested reader can actually Google it, and they will get lot of studies. So, since I am giving this my layout to the foundry who will do the fabrication, so they might insert hardware Trojan in your system, right. So, this is the one of the security risk. The next one is the counterfeiting, is something you have the ICs, you remove the packaging and everything, and then you repackage yourself, right. So, this way you are creating a counterfeit model, and it might so it has commercial benefit, and also it might actually impact some mission critical system, right. So, you can actually create a duplicated kind of counterfeited copies, and you can sell it into market, and you actually have a financial losses to the actual IP provider. So, this is another possible risk. And then the other important things is the reverse engineering. So, this is one of the most important threat, is that you have the IC, you buy something from market, you depackage, you remove all these assembly, the other things, you have the IC, and then you actually delayer and you do some image processing. So, this is a bit involved process, but then you try to see the actual layout structure, right. So, you just see the metal layers, you see the actual structure, and then if you are very expert on that, then you can actually extract the netlist from this, right. So, then what is going to happen, that this is something you have your intellectual property, it will go to somebody else, he understand what is the structure of the circuit, and then what it can does, it can develop his own IC from that, because it has the netlist which you can assume it is in the gate level, and then he can generate his IP, and he can sell in the market, and it can actually can have a huge loss for the original companies, right. So, this is another threat. The other threat is this IP piracy and overbuilding. That is something, as I mentioned, that by doing this reverse engineering, you can actually, this is actually enabled by the reverse engineering, that you have, you ask the first of all is this reverse engineering can do this IP piracy, that they actually delayer and they will get the netlist, and they can actually have this own design from that, right. So, that something is always possible, and but even this foundry, if it is malicious, what can happen if you say you order 100k number of ICs and they produce 300k, right. So, there is no way you can actually detect whether they have produced 300k or 100k, right. So, then 200k they can actually sell it in the market in half price, and because they do not have to invest in doing this, buying these IPs or invest into integrating the things and all the test verification everything. So, they do not have to pay anything and they have the IC with them, right. So, that something is really a concern, specifically this overbuilding and IP piracy. And if you Google it, there are many such news reported in the specifically in the EDA domain and that electronic domain, that there are a lot of such incident actually identified, right. And so, this is something is a real concern. So, in this particular lecture, we try to see how we can actually stop this reverse engineering, and specifically reverse engineering enable the IP piracy. So, this IP piracy and overbuilding. So, how to stop this IP piracy and overbuilding. Okay. So, that something is the hardware security concern that we try to address in this particular class in this particular week. Okay. So, one of the important or interesting solution comes to is the logic locking or logic obfuscation. Okay. So, because what I mean explained so far, that you have to give your IC or the layout to the fabrication lab or the fab, right. So, fab lab, because you do not have your own this foundry, or you have your own lab, I mean fabrication lab, right. So, you have to give it, there is no way alternative, right, you have to give it. And if there is some malicious, either the fab may be malicious, or there are some employee there which has is not trusted. So, you cannot control that part, right. So, then what you have to do, the solution that something this logic locking talks about, that I will give my IC to you, I will give my layout to you, you can do the reverse engineering, you can extract the netlist, you can produce multiple copies, you can duplicate the things and you can sell it market, but that particular IP will not work, right. So, even if you have the whole netlist, you produce IC, you can't use it, right. So, that means I give you my this intellectual property to you, you can do this IP piracy, you can do this overbuilding, but that won't be useful, right. So, that was the motivation of this logic locking. The idea is very simple. The simple idea is something like this, that you have your original circuit. So, suppose this is your original circuit. What I am going to do is that I am going to so this circuit you can see there are 3 inputs and 1 output, say, right. So, what I am going to do, I am going to add some additional input which is called key to the circuit, and I am going to add certain part of the logic into my circuits using this. As a result, what is going to happen, this particular circuit has now this ABC, the original input, and few keys, right. And this particular circuit only will work for a specific value of this keys. For example, you see here. So, if you use the original circuit, you have the ABC. So, it is basically you can see there are 3 AND gate and there is OR gate, right. So, if at least 2 of the input is 1, then the output will be 1. You can understand that, right, because if AB is 1, then this will be 1 and then it will be output 1, BC is 1, then this output will be 1, and if AC is 1, this output will be 1. So, that is not so important. So, this is the circuit, right. Now, what I am going to do, I just added a 2 XOR gate here, right. So, and then I have just added a key. So, now you see, if I give my key equal to 1 here, whatever the output is coming here, it will be toggle, right. So, that is the behavior of the XOR gate. So, now if say suppose you have given the input A, B and C 1 1 0. So, then this, since these 2 are equal to 1, so this will be 1, and since this is 1, this will become 0, right. So, in this circuit it is 1 means output is 1, and here it is 0. So, it is 0, the output will be 0 because the other components are 0, right. So, what you can understand here is so if I give a wrong key K1, then my output will be different, right. So, but if I give 0 here, this 1 will pass and it will come 1 and output will be 1. So, that means the correct value of this K1 is actually 0, and similarly you can understand the K2 value is also 0, correct value. but this K1 and K2 have 4 possible values, right, 1 0 1 1, I missed 1 0 1. So, there are 4 possibilities of this keys, and among them only one of the value is correct, right. So, what I am going to do, I am not going to give this circuit to the foundry, I am going to give this circuit to the foundry as the layout, right. And what I am going to do, I am not going to reveal the correct value of this key, right, because that is only I know. Now, think about if there are 2 keys. So, how he can do that? He can extract, say suppose by reverse engineering he is able to extract this circuit, and then he has to try 4 such combinations, and if he apply 4 such combinations, then only probably he can identify this is something the correct key, okay, say by some say way. But now think about if the key size is say 200. So, how many possibility you have to try? 2 put you are 200, which is impossible, right. So, that means the basic idea is that I am going to create my circuit like this, that I have the actual IC, right. I have the IC, this will I will come from the foundry. So, this is only I am going to give. So, and this is my input, which is the actual input of the circuit, and this is the output of the circuit, right. And what I am going to do, I am actually going to have a extra input which is called key, and this key I am not going to give to the foundry, right. And then once I get the IC from the foundry after fabrication, I will create my system like this. So, I will put a memory which is something tamper proof memory, where I am going to store the key. So, and then I am going to package like this, and this is my system that I am going to give to my customer. So, once you buy it from me, the key is already embedded in your system and it is a tamper proof. So, tamper memory, so that means you cannot go into and check what is the correct value of the key. So, if you buy it from me, then circuit will work, because when I have already embedding my key into the actual circuit that I am selling to you. But if this IC, which is something, if it is overbuilt or after reverse engineering it is produced, the pirated IC. So, this IC has 2 inputs and the key input, and the key is missing, right. So, this key is missing for the this fab lab, because they do not have this access, and it is very difficult to identify if the key size is say 200, 400 or at that range, right. So, you cannot use it. So, what I did is actually this is the difference if you buy from the original vendor and if you buy from the pirated key, because this is missing and you can't use it, but if this key is already embedded in the things I am selling to you, you can just use it, and the customer has no difference, he does not know whether there is a key at all, right. So, because he does not know what is the key and what is the value of the key, he does not need to know, it is actually abstracted from the customer. He will just see that his IC is working, but if you try to sell this, because you do not know the key, your IC will not work, right. So, this is a very simple but very powerful technique, right, because here with this technique I will give my design to you, you can reverse engineer, you get the netlist, you produce ICs, but you can't use it, right. So, all this problem of IP piracy and IP overbuilding can be stopped using this. Hardware Trojan, it cannot be completely done by this, but the other 2 things can be easily done, and that is something is really important, and this actually become very important in the context of this IP piracy and overproducing. As a result, there are a lot of attraction in this in the last 5 or 10 years, right. So, you have to, what is the important point here is that it is something how to, now the question comes into here that I want to lock it, how to lock it, right. So, where which are the places I am going to lock, right, what is the would be my locking logic, right. So, and what will be my key size. So many questions come, and specifically on the logic technique, this locking technique, there are many such things come, and if you look into this in the last 5-10 years history, there are so many important techniques come here, like random logic locking, that was the initial logic locking where you just add this kind of XOR gates. Then there are many other techniques like just anti-SAT, and then you have this SFLL, delay locking. There are many techniques. I am not going to detail of that, because that is a complete different subject altogether, but what I can just tell you that there are a huge set of work happen in this particular area, how to lock your circuit efficiently, right. So, that was something very active research area for last few years, and obviously once you have this locking, attacker don't sit idle, right. So, they try to see that if you have this key, can I extract the key, right, because I know the internal circuit, because the net list of the circuit, and I can buy one copy of this, right. So, from the market, the genuine IC. So, that is called oracle, right. So, I will buy one genuine IC from the market, so that if I give an input, I know what is the correct output, only do not know I can not extract the key, but the actual correct input output functionality I can get it from the oracle, right. So, now I have the internal of this. By doing analysis, checking the actual output and analyzing this, I can probably extract some of the key, right. So, that was the attack technique. So, this is kind of a wire between this attack versus defense. So, you come up with some defense technique, and then the attacker will try to say that even if you lock this way, I can actually extract this using this technique, right. So, this is something a very interesting domain where this work is happening. Okay. So, with this I try to conclude this class, and then what I am going to show that all this locking actually happening in the logic level, right. So, the gate level circuits. So, the question that is important in this course context is that okay, you can do it in the gate level, can you do the whole same thing at the higher level of abstraction, right, at the RTL level or even high level synthesis, right. So, can my high level synthesis do generate a RTL which is already locked? So, that will be great, right, because then you do not have to do anything, you do not have to apply any new technique to lock your circuit, and specifically once you do these things in higher abstraction level, your circuit size will be smaller, right, and as a result you can actually have a more control or the semantic information in the circuit, and you can your locking technique can be very interesting, which cannot be done at the gate level design. Okay. So, with this I conclude this class, and in the next class I am going to see how this logic locking can be done during high level synthesis. Okay. Thank you.